In this video, we're going to look at some more separation of variables differential equation problems that are going to be a little bit less obvious how you can separate them. These are all separable, but we have to come up with some algebraic steps in order to separate the x's from the y's. So in this first example, we've got x plus y in here, and we don't really like to see an x plus y because subtracting is not the same thing as dividing, right? But we can turn this into a multiplication problem, right? E raised to the x plus y is the same thing as e raised to the x times e raised to the y. And if we do that one simple step, then we suddenly see, oh, f of x equals e to the x and g of y equals e to the y. And we now have a separable equation. So the dy will have an e to the y in the denominator because we'll divide that over. And the dx will get multiplied over here. And then we can integrate, which is great. Remember that when we have it in the denominator, the e to the y in the denominator, that means that we're looking at e raised to the negative y in the numerator. In other words, we have e raised to the negative y, excuse me, as our antiderivative, but don't forget the chain rule, or the anti-chain rule, in this case, the little u substitution. You let u equal negative y if you want to go through the process. E to the x anti-differentiates to e to the x. We'll put the plus c on this side. We could leave it like that, or we could solve for y. Let's go ahead and solve for y just for a little bit of extra practice. Divide by negative 1, and we get e to the negative y equals negative e to the x plus c. Again, we don't need to change this to a minus c because adding a constant is the same thing as subtracting the negative constant. Then we're going to get rid of the e by using the natural log. We'll take the natural log of both sides, so the natural log of negative e to the x plus c. And then finally, and notice, by the way, that the plus c is inside the parentheses. And then finally, multiply by negative 1 or divide by negative 1, and we'll get negative the natural log of negative e to the x plus c. Or if you want to get fancy with this, you can say, oh, that negative turns into the negative 1 as the exponent, so we can take the natural log of 1 over negative e to the x plus c, or if you like, you can rewrite it as c minus e to the x. But you don't have to. If you're solving for y, you can definitely stop at this first piece right here. All right. This minus x in this problem seems to be a problem, seems to be an issue that we don't like. We definitely don't want it subtracted from dy dx, so at the very least, let's add this over to the other side. And if we add the x over to the other side, then we can see that there's still a plus going on right here, right? We don't like that so much, except we notice that we can factor this. And if we factor the x out, then we get 1 plus y squared, and then suddenly this is a product of f of x times g of y, and it is now separable. We take the dy, we divide that by 1 plus y squared. We take the x, we multiply it by dx, and we integrate, which is always great, and we get the arctan of y equals 1/2 x squared plus c. And that's a general solution. Or we can solve for y. Solving for y, all we've got to do is take the tangent of both sides and we're done. Tangent of, make sure you put that whole thing in parentheses. We're taking the tangent of the entire expression 1/2 x squared plus c. Not much else you can do with that. Again, these are all general solutions because we're not given an initial value, so we can't solve for the constant of integration. So we'll just leave these with a c in the problem. All right, this next one, kind of the same deal. We've got this minus y squared that I don't really want over there with the dy dx side, so everything else will stay on the left side, but I'll add the y squared over to the right. All right. Now we can definitely divide both sides of the equation by y times 1 plus x squared, and we'll get y squared plus 1 over y times 1 plus x squared. Notice that all of the x's and all of the y's are separate from each other as far as factors are concerned. The g of x function is 1 over 1 plus x quantity squared. The g of y, f of x, is the g of y is y squared plus 1 over y. Okay, so that is separable. You don't necessarily have to write it like that. If you see how you can separate the variables from this line, then I'm fine with that. That doesn't really matter. But we'll go ahead and divide by that y fraction and get y over y squared plus 1 times dy. We'll multiply by dx and get 1 over quantity 1 plus x, that quantity is squared, times dx. And you know that it's great. We're going to integrate. And when we do that, we have to use a little bit of u substitution here. Okay, so we're going to let u equal y squared plus 1. So du dy is equal to 2y, or du is equal to 2y dy, or dy is equal to du over 2y. So when we rewrite this integral, we'll get the integral of y over u times dy is du over 2y. The y's cancel out, which was essential. U substitution requires us to eliminate the original variable. The 2 is okay. It's just going to come out front. We get the integral of 1 over u du, which we should know to be the natural log of the absolute value of u. So when we do all of that, we can see that we get 1/2 the natural log, the absolute value of y squared plus 1. And then on the right side, we could do u substitution with u equals 1 plus x. But notice that the derivative of 1 plus x is just 1. So we really just have an expression raised to the -2. So the inverse power rule is just going to tell us to take that expression raised to 1 bigger. So -2 plus 1 is -1. Make sure you divide by that new exponent. Dividing by -1 is the same as multiplying by -1. And we end up with that as a general solution. And we can solve for y if we like. I don't really love to solve for y when there's a y squared in the mix, because then we have plus or minus. So maybe I'll solve for y squared. Multiply both sides by 2, get natural log. Notice that y squared plus 1 is always positive regardless of the value of y. So I'm going to drop that absolute value bar. And we'll multiply by 2. We're going to get -2 over 1 plus x plus c. We can exponentiate and get y squared plus 1 equals e raised to the -2 over 1 plus x plus c. Remember that just like we saw on that first example in the video with the addition in the exponent, we can turn that into a multiplication problem. And remember also that c is a constant and e is a constant. So if I'm looking at e raised to the -2 over 1 plus x times e raised to the c, this constant raised to the constant is just another constant. So we'll do c times e raised to the -2 over 1 plus x. And then we can solve for y squared by subtracting 1 from both sides. So y squared equals, I don't know, maybe I'll write it as c over e raised to the +2 over 1 plus x. That's an option, not a requirement, but an option. And then I subtracted 1 from both sides, so I'll subtract 1. You can certainly take the square root of both sides, but just remember if you do that, you need a plus or minus, so you can get the top half of the graph and the bottom half of the graph. Unless we were looking at a function that goes through a particular point, then we could choose whether we want the positive or negative version of it. All right, and finally, again, start by moving these terms that aren't being multiplied by dy dx over to the other side. We'll take this term and we'll subtract it over to the other side. So we get x times dy dx equals negative y natural log x. We can certainly divide both sides by x. And we get negative natural log of x over x times y. Hey, it's separable. So let's separate it out. We'll multiply both sides by dx. We'll divide both sides by y. And we all know what's next. How great to integrate. So we will get natural log the absolute value of y on the left side. The right side is going to be a little bit more complicated, but I think we've seen this one once upon a time. If we let u equal the natural log of x, which is not necessarily what we might expect, we'll get du dx equals 1 over x. So that means that dx is equal to x times du. And that's kind of nice, actually. So what we're going to end up with is negative the integral. Let's see, natural log of x is the same thing as u over x times dx. The dx is x times du. So, aha, the x's cancel out, which is always what we need. We need to get rid of the original variable and be left with only the u in our u substitution. So inverse power rule gives us negative 1/2 u squared plus c. And we remember that u is equal to the natural log of x. Make sure you put that natural log of x inside parentheses before you square it. That order of operations matters. And we have the natural log of the absolute value of y equals negative 1/2 natural log of x quantity squared plus c. And again, if you're looking for just any general solution, then that is a general solution. If we exponentiate, the absolute value of y equals e raised to the negative 1/2 natural log of x squared plus c. Or again, that plus c in the exponent can turn into a times c in the coefficient. And notice that now that we've done that, this c could possibly be positive or negative. So we're actually allowed to drop the absolute value bars here because, while e raised to the c could be positive, this c could be negative. So maybe y could equal a negative value. So we get c times e raised to the negative 1/2 natural log of x quantity squared. And I wouldn't mess with that. That looks like about as simple an answer as we could hope for on a problem like this.